Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good evening. This is I'm Eric Horowitz. Welcome to tonight's AAAI Northwest event. Before beginning, just a bit of news from the AAAI. Speaking as the president, I wanted to announce that we've met one of my goals during my presidency, which was taking a serious look at the issue of access to technical publications and the challenges and opportunities that come with the consideration of opening up technical access to technical journals and the digital library more generally. I have to say that after a year of deliberation, the AAAI moved boldly on this, and I'm proud to say that as of this week, all AAAI conference proceedings and technical reports are now available freely to the international research community. And it's a lot of issues were balanced in doing that. We hope other scholarly societies, professional societies, will follow suit. It's the trend, and we think it's actually important even for the success of AAAI over the long term. The AAAI has been having these kinds of evening gatherings around the country over the past year. At the last event in the Bay Area, San Francisco Bay Area, we brought together Sebastian Thrun and Red Whitaker for the first time since they dueled for the DARPA Grand Challenge Prize, and each provided their perspectives on autonomous driving. Tonight we'll focus on what I think is even more important, more exciting issues than cars piloted by machine intelligence. And these are concepts we'll be addressing tonight that cut to the core of all computer science, that provide us with the foundations of computability, where the whole notion of algorithms are introduced and linked to more abstract mathematics. We're honored tonight to have Yuri Gurevich here to tell us about the history of efforts leading up to focused work on the Einschätzungs problem and how Church and Turing pursued key concepts with the ability of mechanical procedures to generate numbers. The work led to what we now call the Turing Machine, a construct that provides us with insights about the nature and limitations of computing. And beyond history, and probably the reason we're here tonight, we'll hear about some exciting new analyses of limitations in the classical work, new results on proofs of computability that Yuri has done with his co-author, Nachum Dershowitz. I'm very honored to talk more about Yuri. Yuri is a principal researcher at Microsoft Research here in this building, where his office is housed. It's nice to do one of these events locally that I've been doing them around the country. He's also professor emeritus at the University of Michigan. He's been honored with the distinction of ACM Fellow and Guggenheim Fellow, among many other awards and recognitions. Yuri was born and was educated in Russia, former Soviet Union, and taught in Israel before coming to the United States. He was a professor at Michigan before coming to Microsoft Research. He's well known for his work in finite model theory and the theory of abstract state machines, of which he's the author. He's also made a contribution to the very challenging area of average case complexity theory. He actually taught me quite a bit about that several years ago as someone interested in what we might know about real-world performance of algorithms, beyond the worst-case analyses we usually learn about in more standard computer science courses. Beyond theory, Yuri has been passionate about computation, computer science in practice, in the spirit of, Boltzmann's statement that there's nothing more practical than a good theory. He's made numerous contributions to Microsoft, where his work has included the use of abstract state machines to build model-based testing tools, including some which are in daily use for conformance testing of Microsoft's protocols. He's helped design efficient algorithms for distributed file replication, including methods that are now used in Windows Server and Instant Messenger. And recently he started to investigate new authorization logics for dealing with distributed data sets knowledge. Here's Yuri to tell us more about the Church-Turing Thesis.
Thank you very much, Eric. And thank you for coming. I have a story to tell And I wanted to start it from antiquity, but then I realized I will never finish. So we'll start it from agenda. So this is, the thesis is the Church-Turing Thesis. So first I'll speak about the prehistory. Once I was told that this habit of giving you agenda in the beginning and summary at the end comes from American Army. Then a little critique and new developments. And we'll start from prehistory, but not from antiquity, from the middle of 19th century. So George Boole formalized propositional logic. And then Gottlob Frege took a much harder challenge to account for what we call now quantifiers, to statements like for all there exist, or some. And that was quite a difficult task. In the middle of this, he receives this letter from Bertrand Russell of June 16, 1902. And Russell writes, Herr Professor Dr. Frege, I enjoyed reading the first volume of yours, and I'm waiting for the second volume. And by the way, here is a little problem. Frege never recovered from that. He discovered a contradiction in Frege's system. So I actually have a hidden slide. It's only 2 lines. But to give justice to the argument would take somewhat longer. So Russell and Whitehead took on a similar task. The idea was, in Frege's work and also in theirs, to derive all mathematics from pure logic. Okay. So there was a kind of philosophical ambition there called logicism, that logic is the primary thing. And in order to avoid the contradictions of the kind Russell found in Frege's work, they stratified sets. So this set can speak about maybe elements. Now that set can speak about sets of elements, but not about sets of sets. If you want to speak about sets of sets, you go there. So the very first level, where you only speak about elements, is called first order. Then there's a second order, third order. So that stratification kept them consistent as far as they thought, and as far as we know till this day. So the problem with their book called Principia Mathematica, one of the most famous books of 20th century and safely one of the most boring. So the one question is whether Principia is consistent. Another is whether their ambition was justified, whether indeed every true mathematical statement can be derived from pure logic. So Principia succeeded in the following way. They only derived a small part of mathematics, in particular arithmetic. However, for the experts, maybe I should tell you, it's often quoted fact, they announce a theorem that 1 + 1 = 2 at the end of the first volume and prove it by the end of the second volume. Because they had to develop all this logic apparatus. But by the end of third volume, they were quite advanced. But of course, they didn't cover mathematics as too big. But for the expert, it was clear, for those experts who had patience to arrive to the end of third volume, it was clear that you can go on and derive almost any mathematics, maybe any mathematics. So building on this, Hilbert posed what is known by the German name Entscheidungsproblem, the decision problem. So the problem is this. Take a logic, for example, Principia Mathematica, or the first order logic. In general, you take axiomatic system where statements have well-defined notion of truth or falsity. So every statement is either true or false. And this is supposed to be well-defined. So take any such logic, take any statement in this logic. So it has to be true or false. Can you algorithmically decide this? So the input is a logic and a statement. The output is true or false. Now, these days, we often pose the question as, is there an algorithm? But at the time, as far as I could see, I'm probably older than many here, but I wasn't there at that time. But as far as I could dig out, the question wasn't, is there an algorithm or not? The question was, find the algorithm. Now, it isn't that he claimed that algorithm can be found quickly. Maybe it never will be found. Maybe it takes centuries to find. But the idea was, find. That was the problem. And as typical of mathematics, okay, you can consider special cases. And the most interesting special cases are Principia Mathematica and first order logic. And then Kurt Gödel appeared. Very young at the time. It took me a long time to find a picture of Gödel where he's young. So he proves that first order logic is complete in the following sense, that every true statement can be derived from the axioms. Notice this does not mean that you have a decision procedure. Why? So you start from axioms, imagine a certain engine, and it derives truths. So if the statement is true, then you eventually will derive it. But if it's false, you will never derive it. So his result solves only sort of half of the problem. This is famous Gödel's completeness result. He was 23 at the time. His second result in 2 years was even more famous. What he proved that contrary to what Whitehead and Russell believed, and with them many mathematicians, it is not the case that every mathematical statement can be derived from logic. So there are statements which can be formulated in Principia, but from the axioms of Principia, you cannot derive truth and you cannot derive falsity. So Principia is incomplete. But his result was much stronger than that. It's not just Principia is incomplete, but tiny portion of Principia. If you just go beyond first order logic, if you have arithmetic, then any system which accounts for that will be incomplete. So it was a devastating result, especially devastating to Hilbert, because he developed certain logical foundation called finitism, which Gödel proved not to be successful. So I don't want to dwell on that famous result. It will take us away. What I want you to note that even though Principia was famous for, at least for the ambition to express most, or at least much of mathematics, the first order logic is of that kind as well. So much of mathematics can be formulated in such a way that it becomes pure logic. So let me say, there is no mystery there. So suppose you have certain mathematical theorem in certain mathematical theory. Now this theory has certain assumptions, so you write them as axioms. And then you say, these axioms imply this statement. So you have to axiomatize the whole theory. And this implication gives you an adequate translation into pure logic. Now, there are problems. Sometimes there is infinite amount of axioms. But in most cases, at least in sufficiently many cases, it works. So after Gödel's result, Hilbert's decision problem was rethought. And by now it is mostly known in that form as Hilbert's decision problem for first-order logic. So given a statement in first-order logic, you want to decide, is it true or false? And when Hilbert asked, find an algorithm. By that time, people began to suspect, especially after Gödel's result, that it is not impossible to have a negative result. So by that time, some people tend to think that maybe the right question is not to find an algorithm, but to ask whether there exists one. Okay. But I'm running ahead of myself. It is that problem that attracted the attention of Church and Turing, and the famous work that they did, it was in order to solve that problem. And if there was an algorithm for that, there would have been much need in having too many mathematicians, because much of the work would be done mechanically. Okay, now I'm moving to the story itself. So let me give away the plot so you'll see what it's all about. So as I said, after Gödel's negative result, people started to think in terms of negative results. And both Church and Turing, but not only them, also von Neumann, some other great logicians of that period, started to suspect that maybe there is no algorithm of the kind that Hilbert wanted. Now, how can you possibly prove that? How can you prove there is no algorithm? So one way is to define what an algorithm is. But there is an easy way to find a system of algorithms which is sufficiently universal in the sense that if no one algorithm in that system solves the problem, that no algorithm at all will solve the problem. But you see, there is a gap between general algorithms and algorithms in your system. Okay. So now with this background, I come to the story. At that time, Church was a professor at Princeton. And Gödel was in Princeton as well. Let me see. Maybe I'm not so sure. He was in Princeton after the war. But in that time, maybe they exchanged letters. Let me don't state something that I'm not sure. So in any case, Church was working on Lambda notation. So what is Lambda notation? He didn't invent it, but he was fond of it, and he pushed it very far. So let me say, what is a Lambda notation? Suppose you have this, a plus x squared. So you can write it in high school. What does a plus square mean? Typically, people mean that a is a constant and x is a variable. But it's a convention. Can we make it precise? And the answer is yes. So you write this lambda x, and lambda x turns this expression into a function of x. So now lambda with the square brackets is a function. So you can apply this function. Suppose you apply this function to 2. 2 goes instead of x, and you get a plus 4. That's the lambda notation. So Church wanted to compete with Principia, and probably more important, with set theory. So Whitehead and Russell were philosophers. And then there were mathematicians who didn't care much about philosophy. He probably didn't read Frege. And they developed set theory from mathematical consideration, starting from Cantor. And by 1930s, set theory was gaining acceptance would be understatement. It was quite recognized theory. And Church wanted, instead of sets, to work with functions. He had 2 great students, Kleene and Rosser, and he put them to work on his system. And sometimes it's very dangerous to have good students. They demolished his system. They proved that it's inconsistent. So here is a very partial list of logicians who published systems later proven to be inconsistent. So the list looks like an honor roll. So Rosser himself, as you see, is at the end in the same company. But Church was not like Frege. He didn't collapse. He was a very sane man. So he took a safe portion of his system, in fact, provably safe, and created what is known now as lambda calculus. So now many people work on lambda calculus. I should say that the story of logic is very much related to modern computer science. So I mentioned type theory that Whitehead and Russell invented. And of course, type theory plays enormous role in functional languages and in programming languages. Similarly, lambda calculus is quite popular in some mostly theoretical computer science today, and Church considers to be the father of lambda calculus. So he created lambda calculus and now his goal was different: to disprove Hilbert's I don't want to say conjecture, the way Hilbert formulated, to prove that there is no algorithm for deciding first-order logic. So it took him and his students a few years, and they developed elaborate machinery. It's a very strange calculus. So they were able to express a lot of functions, and there was a stumbling block. They couldn't prove that n minus 1 is expressible in lambda calculus. And so there's a story of Kleene who came with this idea being in a barber shop, and so he ran out because he understood suddenly how to express. But eventually especially Church convinced himself that any computable function can be expressed in lambda calculus. Now, by that time, Gödel was in Princeton. What I'm not sure when he relocated there permanently. But in 1934, he was there because he gave very famous lectures in the winter semester of 1934. So Gödel was in the institute, and Church was in the university. So Church comes to Gödel, and with this thesis. He actually called it a hypothesis. It was Kleene who later renamed this hypothesis to thesis. Church wasn't...
Was Gödel there in 34?
Say it again?
Was Gödel in Princeton in 34?
Yes.
Well, he couldn't have been at the Institute. The Institute was formed after the war.
Good point. Yes, thank you. So he probably was at university at the time. Okay. So Gödel finds this idea thoroughly unsatisfactory. So why should I believe you? Now, let us come back in a few years. There are many ways to write algorithms. One of them is recursion. And one of the most common recursion is illustrated here. So you define a function, in this case, a functorial. So you define f of n plus 1 using the value of function at n. Okay? These days, this kind of recursion called primitive. At the time, it was the only known recursion. And it occurred to Hilbert that maybe it is very general. So he asked his students, are there a computable function which cannot be defined using this primitive recursion? And he has 2 students who worked on this. In fact, 3, but these are the more people with more famous results. So Wilhelm Ackermann, it should be 2 N's, came with a counterexample, famous counterexample that in textbooks today. Now, Rosa Peter actually did a much more fundamental work. What she dug out that in addition to this primitive recursion, which when you go on one parameter, you recurse on one parameter. There is a kind of 2-dimensional recursion and 3-dimensional, and there are other complications. So she wrote a book. As a student, I by chance bought Russian translations of her book, and it's a great book. And so it was a zoo of all kinds of recursions, more and more powerful. So why do I tell this story? Because in the winter semester of 1934, Gödel gave a course of lectures. And he asked this question in the course, whether every computable function can be defined by some kind of recursion. And his own answer was, it seems to be so, but you have to use not only primitive recursion, but all kind of recursions. So, by the way, I'm telling this story using a fascinating article by Martin Davis called "Why Gödel Didn't Have Church's Thesis." And Davis says that these two events, which I called Act 1, when Church came to Gödel, and when Church said that in his lectures, difficult to place which of them was earlier. So they were roughly simultaneously. By the end of the course, Gödel worked out a recursion calculus of great generality. All the recursions of Rosa Peter were there. And any other kind of recursion that was known on numbers. We speak only about integers here. On integers, it seems to be there. And Martin Davis said, at that point, Gödel could have pronounced a thesis, but he didn't. So Act 3, Church and Kleene prove that Gödel's recursion calculus and their lambda calculus are equivalent. So take any expression in lambda calculus, which you can think about a program for computing a function from integers to integers. There is a systematic way to transform it into an expression in Gödel's recursion calculus, and the other way around. At this point, Church didn't consult Gödel and announced his result on a meeting of American Mathematical Society. So Church's thesis became public in this form. It's interesting that he used that form. He used Gödel's recursion calculus rather than his own lambda calculus. Apparently, he thought that that's somehow more appealing. Act 4, Church publishes his thesis and proves Hilbert decision problem. So what he actually proves that there is no function which can be expressed in Gödel's recursion calculus which solves, which gives the decision procedure for first-order logic. Okay. So let me recall, what was the problem? We want an algorithm which takes a statement in first-order logic and decides, is it true or is it false? Okay. So he proves mathematically that no function, no expression in Gödel's recursion calculus can program such a decision procedure. And then he uses his thesis to say there is no algorithm. Because if there was any kind of algorithm, then there would be a computable function which gives the decision procedure. So his thesis was this bridge. By the way, I don't mind to be interrupted if you feel like that. And then there was Turing. Back in England, working alone as far as we know. And he wrote a stunning paper. So it was analysis of a computer. Now, what kind of computer? This is 1930s. The computer was a mathematician. Turing calls a mathematician a man. So it's a man. So what Turing did, he said, okay, suppose we have computable function, any computable function, from integers to integers. In his case, actually, from strings to strings. So there is some kind of algorithm that computes. Remember that algorithm is a man. So he says, how does this man compute? So how does mathematician compute? He has a piece of paper. He writes something. He goes back. He looks up. He looks forward. So without loss of generality, he says, the paper is like an arithmetical paper for children. Without loss of generality, in every square only one symbol is written, and so on. He goes, and after, I don't remember, a dozen or so, without loss of generality, he arrives to a Turing machine. And arrives to what today it's called Turing's thesis. Now, he didn't call it a Turing machine. He's a modest man. And he didn't call it a thesis, but it's known now as a Turing's thesis. Every computable function is computable by Turing machine. And he also derives the negative results. That's what prompted them in the first place to solve Hilbert's decision problem. When he submits his work, he learns that Church already published this. So nevertheless, the work is accepted, and he adds an appendix. And in appendix, he proves that his thesis and that of Church are equivalent. So if you take one for granted, you can prove the other one, and the other way around. Or simpler, take a Turing machine which computes some functions from natural numbers to natural numbers. There is a program in Gödel's recursion calculus which gives you the same function, and the other way around. Church writes a review, and he was a gentleman. He starts his review with stating clearly it was an independent investigation. He also acknowledges that Turing's approach is more convincing. And then he says something that his approach also has some advantages. And everybody accepts Church-Turing thesis, including Gödel, the great skeptic. Okay, that concludes the story. Now, critique. So the thesis became accepted universally. There are some crazies here and there who doubt, or at least only crazy seems to publish something about their doubts. But if you ask people who think about such things, of course, most people don't think, and there is nothing wrong in that. In a sense, it's even complementary. You know, sometimes people who work in foundations complain that people, don't give enough thought to foundations. But in fact, it's a compliment because people trust you. You have a good foundation. In any case, but if you ask people who do think about such things, why do they believe Church's thesis or Turing's thesis? The most common result that there are so many different models. And indeed, after Church and Turing published their papers, a great many models appeared. And they all were proven of computability, and they all were proven equivalent. In fact, the very first model by Emil Post from the City University of New York appeared before Turing, right after Church, but before Turing, in this just few months there, in this period. So I have a problem with this argument. First of all, it's not that many independent problems. So there was Lambda calculus and recursion calculus in Turing machines, and that's about it. The others were derived, at least conceptually. These were different forms, but not truly different. But even if there were hundreds of different models, and they all coincide, it's only proves that the notion captured by those models is robust. It does not prove that the notion is right, because there could be a systematic mistake that all of them make. Another argument is that there are so many years of experience. And of course, with each additional year, there are more years of experience. This argument is also not so strong. Popper writes, Karl Popper, in one of his books, that imagine you live in a low country, low, like Netherlands, not in the mountains. And the water boils at 100 degrees centigrade. Okay? And these people may live there for centuries. And there's a lot of experience until they climb a mountain. So really, the most convincing argument for the thesis is still Turing's speculative analysis. And this analysis is very powerful. Turing was far from a pedant. So his analysis in this paper and in other papers, it's a kind of broad sweep. And when you read, like you go to opera and you are overtaken by music. So somehow he overtaken by this grand sweep of his vision. But if you take magnifying glass and start to look closer, then certain question may arise. But let's see, I'm going ahead of myself. Before I go there, let me mention that there seems to be one additional attempt to analyze computation. So there is a talk by Kolmogorov in 1953, and there is a paper with a student of his in 1958, where they define so-called Kolmogorov machines. Some very interesting machines. There is no philosophy there. It's not clear where they were coming. But a favorite student of Kolmogorov, Leonid Levin, who teaches at Boston University, tells me that what Kolmogorov had in mind, a different kind of analysis. So Turing analyzed a person doing a computation, performing a computation. What Kolmogorov seemed to be thinking was computation developing in time and space, and especially in space. So every element is somewhere in the space, and in the close vicinity there could be only so many other elements relevant to the computation. So quite an interesting idea. There is a little flaw. Kolmogorov machine doesn't fit in 3-dimensional space, or 17-dimensional space, or any finite dimensional space. So it got to be very generalized kind of space. It was a very interesting advance. Let me mention some other aspects. Turing machine, contrary say to Church, Turing machine allowed us to count steps, and therefore it was the beginning of modern theory of complexity. Kolmogorov machine gave birth to another kind of complexity. So he asked the question, and possibly a rhetorical question in his seminar, Kolmogorov. can you multiply numbers quicker than the normal method? And you cannot ask this question on Turing machines because they're so clumsy, it just doesn't make any sense. But Kolmogorov machines were much more advanced, much closer to a computer of today. And surprisingly, the answer was yes, you can multiply faster. Okay, but that's a different story. So the question is, what exactly did Turing assume? And that was not so obvious. So if you go through his argument, he speaks about a person. So at a certain point, he says that there is only finite many states of mind. Finite many states of mind as far as performing algorithm is concerned. Suppose you perform certain algorithm. Now you can stop, go for a lunch, you can return, you resume. You can even leave some note and ask somebody else to continue. So it seems convincing, but it's hard to put it as a mathematical axiom. So Gödel thought about another approach, that it may be possible, instead of analyzing anything particular, just start from axioms. That was one reason I wanted to start with antiquity and Euclid, when you start from the birth of axiomatic method. So you start from axioms, you postulate certain general properties of computability, hopefully acceptable to all, and then maybe you establish that indeed every computable function is Turing computable. So another part of critique. The thesis succeeded so much that people often identify algorithms with Turing machines. So there are books of very respectful authors where they just say that by definition an algorithm is a Turing machine. And this is wrong. There is much more to an algorithm than the function it computes. So, the algorithm may have certain idea. There is a level of abstraction, data structure, certain complexity. Many things will be erased. So I'll give you a very simple example, at least if you remember how do Euclidean algorithm, how do you compute general common denominator? And Euclid himself did it via differences. Today we do via division. Now, if you try both versions, which are quite different, if you try to write Turing machines for both of them, first of all, you have to do something about division. What we will do about division, you'll implement it as difference. So the distinction between two algorithms will be erased by the time you arrive to Turing implementation. Let me notice this. So in this lecture, I speak about algorithms in the classical sense. So Kolmogorov said it quite well. Algorithms compute in steps of bounded complexity. In steps of bounded complexity. So each step is small, and you compute step after step. So today we speak about distributed algorithms, real-time algorithms. So here we speak about classical kind of algorithms. So there are such algorithms that compute in steps of bounded complexity that cannot be implemented at all on Turing machines. So here is one example, courtesy of Professor Reisig from Humboldt University, somewhere here. So it's a geometric algorithm from times of Euclid. So you have a circle with a center P, here, circle and center P. And you have a point outside. And the problem is to construct a tangent like that. That's the problem. And they had quite a nice algorithm for this. So here it is. First, you connect P and Q with a line. You know, they did this with a ruler and what is the standard expression? Compass. Ruler and compass. By the way, sometimes people wonder, why ruler and compass? Couldn't they understand, that there's also ellipse and something else? They could. They understood it very well. But ruler and compass was their computer. It was their true computer. They really computed that way. And that's why it was so important for them to do with ruler and compass. And so all these operations can be done with ruler and compass. So you put this line, you find the middle point, then you take the circle, then you take a point there. There is another point. And then you connect. That's the algorithm. Can you do it on Turing machines or in C? So not every algorithm even Turing computable, not even input-output relation. Oops, let's see, did I miss another one? No. Okay, I will show another algorithm of that sort later on. So now we come to new developments. So this part is a bit more technical. So the bottom line, we implement what Gödel was proposing. We propose certain principles, hopefully acceptable to people, and derive the thesis from those principles. Okay, that's the bottom line. Analysis. So when I started in the early 1980s, quite a while ago, when I came to Michigan, I moved from mathematics to computer science, and I wanted to understand what do they do in computer science. And I arrived to a conclusion that what they do are algorithms. Operating system is an algorithm. Compiler is an algorithm. So it seems to be all about algorithms. Now, what is the mathematical apparatus to deal with algorithms? So in physics, you use differential equations to speak about physical processes. What are the differential equations of computer science? So we had this Turing model, but it seems utterly inadequate. Not taking away from the glory of great Turing, but he made an enormous advance. But the model was inadequate for our days. So I was thinking maybe we can have much more powerful model. So what's the problem with Turing machine? The problem is that you deal on the very low level of abstraction. You deal with single bits. Now, at the time, there were very sophisticated programming languages like PL1. You can take two matrices of arbitrary dimensions, same dimensions but arbitrary, and multiply them at once. Now, poor Turing machine will walk painfully for a long time to accomplish the same result. So can you have a computation model which will live on the same level of abstraction as the reality you deal with. And it seems to be too good to be true. Now, if it works, then there are good uses for this. For example, you write software specs. You think what your software is supposed to do, and you write something on that level. So here is, as they say in German, Gedanken experiment. Suppose there is such a model. How would it look like? And this way, it's a long story, again, a separate story. I arrived to a versatile model, which are called abstract state machines. So here is an example. And that's another example of something the Turing machine cannot compute at all. And again, courtesy of Professor Reisig. So what is the problem? This is not from antiquity, that's from 19th century. So you have a continuous function. You want to find a point close to the zero of this function, to the root. So a point where this function is zero, called the zero of the function. So you don't necessarily find the point itself, that's much too complicated. But you want to arrive to the vicinity. So you start with certain epsilon, you want to arrive to epsilon vicinity of that point. And the algorithm is very simple. So you start from points A and B such that a function at A is less than at B. Then you take the median between A and B, and you check what happens with the function. If you're already close enough, fine. If not, you see what's the sign. If it's positive, okay, this will be the new B. Okay? You do another step, find another function. Okay, this will be a new A. And you keep going. And of course, your interval shrinks exponentially fast. And function is continuous. And by classical theorems, you solve the problem. And here is, so this is an initial condition. And here is a program in the language of abstract state machines. It's a kind of theoretical language. The whole program is one step. And you repeat this step like with Turing machine. Repeat until you finish. So, and that more or less says what I explained. As you see. So you compute the median, and if you close enough, you output the median and halt. Otherwise, you check where you are, and you redefine A or B. So later, in fact, when I joined Microsoft 10.5 years ago, I was able to write axioms for the notion of algorithm. And that's what the next part of the story. So there will be 3 axioms or postulates. So one of them is an algorithm computes in steps. It's a kind of triviality, but you have to say it. Axioms often looks very trivial. In fact, the more trivial, the better. The axiom is supposed to be obvious. And obvious can be pushed. There's a story of a math professor who gives a lecture and says, this equation is obvious. Okay, most people write, it's obvious. And there's one clever fellow who raises a hand. Is it really obvious? Professor starts to pace the floor. Goes in the corridor, paces the floor. comes back, says, yes, it's obvious, and continues. So now, with this postulate, just two problems remain. One problem is, let's see, when I say it's a transition system, you go from one state to another, and transition is going from one state to another. So two simple problems: what are the state and what are the transitions? And if you allow me another joke, that one goes to Dan Knuth, presumably. I haven't heard this joke directly from him, but it was attributed to him. And he said there are two main problems in AI. And they are, what is A and what is I?
The previous story was contributed by physicist to Paul Dirac.
Thank you.
So they said.
Your wealth of information. Okay, now what are the states? So a state, if you think about a computation, what's a state? A state is certain information which, together with a program, completely determines all the future as far as computation is concerned. So this is a very natural definition of state, and it's very different from the one given in books. So why? Typically in books, if you go, say, to a textbook on C, they would say that state is given by the values of the variables. And that's a very different notion of state. The values of the variables do not determine future computation. Why? First of all, you have to know where you are in the program. Then you may have a stack with frames, incomplete computations, which eventually come into play, and so on. So our definition of state is a completely transparent state. So state is such that it determines the future of computation completely. Okay. Nothing is hidden. So by the way, that's why semantics of programming languages is so hard, because they want to present a simplified point of view to you. So when you program in C, you just see few variables. And you don't think about all this unfinished computation that you put into stack, or in C# or in Java that are on the heap.
Would you admit a simulation, a random variable?
Say it again?
Would you admit a simulation, a step that called a random variable?
Yes. So I'm speaking about deterministic computations, but if you speak about non-deterministic computations, then it will be not the future of the computation, but the full variety of possible computations. Mm-hmm. So here's the second postulate. I wanted to be very sure that copyright is okay, and so it picture of one of my daughters, and she gave me her permission. Okay. So the second postulate says that states are what logicians call structures. So if you don't know, it's very easy to define. It's a set with operations and relations. But truly appreciate the notion of a structure, you have somehow to work with this a little. But mathematicians don't speak about this, but I think it's fairly common that people would agree that any static reality can be described as a structure. Okay? So if you go to math department and fetch the first mathematician, ask what he's working on, it will be some kind of structures. Maybe graphs, it could be Hilbert spaces, but some kind of structure. I don't necessarily mean the structures are finite, whatever they are. So this is conceptually the deepest postulate. So in the abstract part is that this in structure is that you don't look from what elements are made. So let's say, suppose you have a graph, and you say, but what are the elements of the graph? What are their ideas? There are no ideas. So for those who know Lisp, when you study Lisp, before you start, use quotes. So that's very clean. There are those atoms. They have no identity. They're just atoms. Okay. So that kind of structure. So the only information is given by operations and relations. The elements themselves have zero information. They're just points. And that's the abstract part. That's exactly what allows us to go to any level of abstraction where we want to be. And the finite postulate solves that problem that Kolmogorov sort of informally posed, steps of bounded complexity. How do you say that step is of bounded complexity? It's a very different kind of complexity, like polynomial or something, because when you speak about polynomial complexity or exponential, it's the number of steps. But here we have one step. So the intuition is, let's see, imagine a huge state, and you are a little ant, and you make a transformation, one step, and you see just a little bit around you. You don't see the whole state. Okay. And that postulate took me like 15 or so years to arrive at.
Clarification on this. Does this mean that, for instance, beta reduction in lambda calculus or unification, would they be considered bounded exploration as well?
No.
Okay.
No, because beta reduction can take term of arbitrary width, so this is not.
Okay. So it's not just termination; it has to be absolutely bounded. By
Bounded, yes, at every step. Much depends how do we look at it. If we go to very high level and we say terms are elements having no structure, then it may be different. It much depends how do you look at it. So it's all relative. You take certain level of abstraction and you see what happens on that level.
Well, maybe you would admit like a kind of a more detailed beta reduction that would,
yes,
in every step change a little bit, as long as it's the same behavior.
If it's doable, I'm not sure. Mm-hmm. Yes, but you are on the right way. So the last postulate says that there are certain expressions in the language. So let me say where I'm coming from. So we have the state. And state is a structure. There are these operations. Relations are also operations. They're just Boolean valued operations. So all you have these operations. Suppose I want to say, give me that element, or just to point to some element. How can I point to an element? I cannot say element whose ID is 17, because they don't have any IDs. So the only way for me to point to an element to have an expression. Okay? So for example, if in arithmetic, if I have expression 0, which already points to one element, and I say successor of 0, that's why I can point to a particular element that we call 2. So there is a fixed number for a given algorithm, fixed number such of expressions. And during one step, algorithms only evaluates these expressions, nothing else. It doesn't see anything else. So how can you say that you don't see anything else? Okay. And the idea is that the change that you make depends only on these expressions. And I'll give you an example. Let me see. Coming back to this program. So what are these critical terms or expressions here? They are, let's see, first of all, this expression, b minus a over 2, which we just call m, but the expression is this. Then there is this Boolean expression, the whole thing. It may be true, may be false. Then this expression, and I think that's it. So imagine you have two functions which coincide here but may be very different outside. But then the process described here will go exactly the same way. We just don't care what is outside. We never see it. Mm-hmm. In fact, you may have function which is different here, but we will miss it. Mm-hmm. Okay, so let me go. So more or less on time. So that allows to define algorithm as any transition system subject to these two. Postulate, abstract state, and bounded exploration. And that allows to prove this representation theorem. So if you take an algorithm in that sense, so anything satisfying the three postulates, then there is an abstract state machine which, as transition system, is exactly the same. Same state, same transitions. Behaviorally, there is zero difference. Okay. At that point, Nachum Dershowitz was visiting here. Oops. Back to church. And so he was already for a while working on these abstract state machines. And so he brought, maybe we can actually use these axioms. Now, in my mind, I came to Microsoft. I'm not a mathematician. I'm, computer guy. And my purpose was to do something useful. And indeed, we use this abstract state machine theory. And we have a tool called Spec Explorer, which was shipped internally and used in Windows. And so all my direction was, this part of my life is engineering. And in fact, I didn't even think, never heard of this problem. And we started to think. And turns out that these three postulates are sufficient to define algorithms, but they're not quite sufficient to derive the thesis. We need a little bit more. And that's what we did in this paper. So let me remind what the Church's thesis is. So why churches? So we had this choice to prove in a kind of very pedantic way, Church's thesis or Turing's thesis. And Church deals with arithmetic, where things are much more standard. Everybody knows what's arithmetic. 0, 1, multiplication, addition, multiplication, division. That's it. Now with strings, different groups have their own basic operations. So we went with the easier case of arithmetic. So what you want to prove? That every computable numeric function is expressible in Gödel's recursion calculus. So now how do we want to prove it? Now we have a notion of algorithm. So we want to prove there is no algorithm, just directly. So here's clarifications, what numerical functions. I said from integers to integers, historically they considered, didn't want to deal with negative numbers for no particular reason, it's just tradition. and functions may be partial. So that's Gödel's program, or Gödel's approach. And so the one additional postulate was needed. So you see, ASMs are so powerful, you can define this geometric algorithms and algorithms on continuous functions, or functions are not necessarily continuous. You can work with Hilbert spaces. But Church wants to work on integers, with integers. And so you have to start from something very specific. And so our additional postulate has this form. Okay, we didn't. So we put something which that everybody agrees is computable. So in fact, 0 and successor are sufficient. Okay. Or you can put 0, successor, plus, and multiplication. And then call an algorithm satisfying the 4 postulate arithmetical. And then it becomes a theorem. So Church's thesis becomes a theorem in this framework. Similarly, we can prove from scratch Turing's thesis, but we need to modify this postulate. So instead of arithmetical algorithms, we need string algorithms. And this can be done, and you get theorem 2. And that's it. Thank you.
Thank you very much, Yuri. Any questions at this late hour? Certainly tantalizing enough to be debated.
Yes. Yeah.
I had more of a clarification question. So you said, what about probabilistic algorithms? For instance, the primality testing algorithms or something like that. Are these covered by this framework, or are they beyond the scope of this framework?
They are covered by this framework. So let me explain how. Instead of randomization, I'll speak about non-determinism, but same issue. So the question is whether non-deterministic algorithm is an algorithm. And if you think about it, it's a contradiction in terms. How non-deterministic something being an algorithm. Let's see, there is Yogi Berra has one of his saying is, when you come to intersection, to a fork, take it. Okay, here is an algorithm, very clear algorithm, non-deterministic, and obviously there is something wrong with it. So it is, indeed, algorithm cannot possibly be non-deterministic. So what happens, how do we have non-deterministic algorithms? So algorithm needs help. So for example, in C, when you say E1 gets E2, according to the manual, you can evaluate E1 first or E2 first. And it matters. You know, in good programming, it shouldn't, but it may. Okay. So which one do you take? The C itself doesn't know. The compiler should help it, and compiler does help. Okay. Or, for example, in C# or Java, you declare an object. And an object appears. Kind of very non-deterministic. How does it appear? Who made it? It's a lot of work goes to create an object. You need to allocate space, you can put certain kind of things. So in fact, when algorithms says, you know, new object of that class, such and such, it's really SOS. And an operating system comes and helps. Okay. So in that sense, so when you also incorporate the helpers, so two ways to deal, and we dealt with them both. One way to incorporate a more complicated system together with the helpers. Okay. And another approach is to consider interactive algorithms, which openly, send the query and wait for the result, and so on. Okay. More questions?
We'll conclude there. Thanks very much for your interesting thoughts tonight.